Look at this race car. Wait, no, not a literal race car. I mean the word race car. Is it a palindrome? Does it read the same forwards and backwards? Yes. To verify it, you check the outer letters, work your way to the middle, and see that it matches perfectly. Now, look at this string. X race car X. Is that a palindrome? Pay attention to what your brain just did. Did you check the R's, the A's, and the C's all over again? Of course not. You already knew the middle part was a palindrome. You only checked the two X's on the outside. You took a complex problem, realized you had already solved the hardest piece of it, and just reused the answer. When humans do this, we call it common sense. When a computer does it, we call it dynamic programming. It's the simple idea of never doing the exact same work twice. And while it sounds obvious, it is the single most powerful optimization technique in computer science. It's what makes your GPS instantaneous. It powers DNA sequencing, and it's the secret behind half the hardest coding interview questions. Today, we're going to demystify it forever. Alright, so what exactly is dynamic programming? Let's skip the textbook definitions for a second. At its core, dynamic programming is just a really clever way to solve big problems. You break the problem down into smaller pieces. You solve each piece exactly once, and then you just remember the answer. That way, you never have to do the same work twice. It's really just 3 steps. Break it down, solve the pieces. Remember what you've solved. And honestly, this isn't some crazy exotic technique. You actually do this all the time. Think about adding up a grocery bill in your head. You see $3 plus 7 plus 2 plus 8. You've got 20. Now let's say the cashier scans one more item for $5. You don't suddenly over from scratch, right? You don't go all the way back to 3 plus 7. Of course not. You already know the running total is 20. You just add 5 to it and boom, 25. That's dynamic programming. You just remembered the result of the work you already did and you reused it. The reason this is such a big deal in computer science is that a ton of problems have this hidden trap in them. If you take a naive approach, your code will end up solving the exact same smaller problem over and over and over again. And that wasted effort, it blows up exponentially. Let me show you what I mean. Take a look at calculating the Fibonacci sequence. If we want to find Fibonacci of 10, we first need to figure out Fibonacci of 9 plus Fibonacci of 8. But to get Fibonacci of 9, we have to calculate Fibonacci of 8 plus Fibonacci of 7. Wait a second. We are already calculating Fibonacci of 8 over on the right side. But the computer doesn't know that, so it just blindly calculates it all over again from scratch. And it just gets worse the further down you go. The deeper the tree gets, the more these duplicates pile up. F of 7 ends up being calculated 3 different times. F of 6, 4 times. By the time you're done calculating just Fibonacci of 10, using this naive method takes 177 separate function calls. And almost all of them are completely redundant. Now watch what happens when we use dynamic programming instead. We just start from the bottom. F of 0 is 0. F of 1 is 1. Those are our starting points. Now f of 2 is just f of 1 plus f of 0. 1 plus 0 is 1. We store that. F of 3 is f of 2 plus f of 1. 1 plus 1 is 2. Store it. F of 4, f of 3 plus f of 2. 2 plus 1 is 3. Store it. You see the pattern here? Every single step just looks back at the 2 answers we already figured out. We aren't recalculating anything. There's 0 wasted work. We just sweep straight through the table, and we're done in exactly 9 steps. So, naive recursion, 177 wasted calls. Dynamic programming, just 9. It's the exact same problem and the exact same answer, just a completely different and way smarter approach. And that is the power of remembering. So DP is powerful, but you can't just use it on every problem you come across. There are 2 things a problem needs to have before DP is even worth trying. And once you know what they are, you'll start spotting them everywhere. The first one is called overlapping subproblems. And let me show you what that actually looks like. Say you want to compute Fibonacci of 5. So you break it down. f of 5 needs f of 4 and f of 3. Then f of 4 needs f of 3 and f of 2. Then f of 3 needs f of 2 and f of 1. And this just keeps going. But if you look closely at what's happening, f of 3 is being computed twice. F of 2 is being computed 3 times. F of 1 shows up 5 times. You're doing the exact same calculation over and over and over. And that's basically what overlapping subproblems means. When you break a big problem into smaller pieces, the same smaller pieces keep showing up. And you end up wasting a ton of time resolving things you've already solved. What DP says is instead of solving each subproblem every time it comes up, just solve it once, store the answer, and look it up the next time you need it. That entire tree with 15 function calls collapses down to just 6 unique subproblems. And keep in mind, this is only Fibonacci of 5. Imagine doing Fibonacci of 50 without storing anything. You'd be waiting a long time. So that's the first thing your problem needs. It has to be repeating the same subproblems. The second thing is called optimal substructure, and it sounds intimidating, but it's honestly a pretty straightforward idea. Say you've got a graph with nodes connected by edges, and each edge has some cost. You want to find the cheapest path from S to T, and turns out the cheapest route goes S to A to B to T, and the total cost is 2 plus 4 plus 2, which is 8. Now here's the important part. Look at just a chunk of that path, the path that goes from S to A to B. That costs 6, and that chunk has to be the cheapest way to get from S to B. Because if there were some cheaper way to get from S to B, like going through C instead, then you could swap that cheaper chunk into your overall path and get a lower total, which would mean your original path wasn't actually the cheapest, so it's a contradiction. The best overall solution has to be built from the best smaller solutions. And that's all optimal substructure means. The best path from start to finish contains the best paths between every pair of stops along the way. So when your problem has both of these things, it keeps running into the same subproblems over and over. And the best answer to the whole thing is built from the best answers to the smaller parts. That's exactly when dynamic programming works. That's the signal that tells you DP is the right approach. Okay, so we know what DP is, and we know what to look for. But honestly, knowing the theory doesn't actually help until you can use it. Let's work through a real problem together. And as we do, I'm going to show you a simple 5-step process that works for pretty much every DP problem you'll ever see. Here's the setup. You're given a bunch of coin denominations and a target amount, and you need to figure out the absolute minimum number of coins to hit that exact amount. You can use any coin as many times as you want. Let's make it concrete. Say your coins are 1, 3, and 4, and your target is 6. Now, if you just use 6 1 coins, that technically works, but it's super wasteful. You could do 4 plus 1 plus 1, which brings it down to 3 coins. But if you just use 2 3 coins, you hit 6 with only 2 coins, and that turns out to be the best you can do. Now here's a fun trap a lot of people fall into. You might be thinking, why not just always grab the biggest coin that fits? That's called the greedy approach, and it sounds really reasonable at first. But let's test it. Imagine a different set of coins, 1, 5, 12, and 25, with a target of 36. The greedy strategy says to start with 25, then throw in a 5, another 5, and a 1. You end up using 4 coins total, which seems decent. But if you just use 3 12 coins, you also get 36, and that's only 3 coins. Greedy completely missed the optimal solution. That's exactly why we need something a bit more principled, which is where dynamic programming comes in. Alright, step 1. Visualize. Whenever I'm stuck on a DP problem, the very first thing I do is try to draw it out to look for structure. Think about what's actually happening when we try to make 6. Right before we place our last coin, we must have been at some smaller amount. If our last coin is a 1, we were at 5. If it's a 3, we were at 3. And if it's a 4, we were at 2. Each of those smaller amounts can be broken down in the exact same way, which is already a huge hint that we're dealing with a recursive structure here. This is where a really useful model shows up, the directed acyclic graph or DAG. Picture every amount from 0 to 6 as a node, and draw an edge between 2 nodes whenever you can jump from one to the other using a single coin. Any valid way of making change is now just a path through this graph. And the minimum number of coins? That's literally just the length of the shortest path from 6 down to 0. We just turned a vague question about coins into a concrete graph problem. And that kind of reframing is exactly what makes hard problems feel manageable. Okay, step 2. Find the right subproblem. This is honestly the make or break moment. If you pick the wrong subproblem, nothing else is going to work. But if you get it right, everything just falls into place. So, what's the thing that's actually changing as we work through this? It's the amount. The amount keeps shrinking as we use coins. So, a really natural subproblem is to define C of n as the minimum number of coins needed to make amount n. C of 0 is 0 because you don't need any coins to make 0. C of 1 is 1 because you just use a single 1 coin. And our ultimate goal is to find C of 6. Moving on to step 3, finding the relationship. This is where it gets really fun, because now we need to figure out how these subproblems actually connect to each other.
Think about C of 6 for a second. If we decide to use a 1 coin as our last coin, then we need to already know C of 5. If our last coin is a 3, we need to know C of 3. And if it's a 4, we need C of 2. So C of 6 is simply 1 plus the minimum of C of 5, C of 3, and C of 2. We're just picking whichever previous amount needed the fewest coins and adding one more coin on top of that. Step 4. Generalize. There's nothing really special about the number 6 here. This exact same relationship holds for any amount. For any amount n, the formula is C of n equals 1 plus the minimum of C of n, minus whatever coin we choose. One single formula that handles any target and any set of coins. And finally, step 5, implement. This is where we actually fill in the answers. The key insight here is that we need to solve our subproblems in the right order, meaning every subproblem we depend on should already be solved before we get to it. For this problem, the order is super straightforward. We just go left to right from C of 0 up to C of 6. We start with C of 0 equals 0. Then, for each amount from 1 to 6, we try every possible coin and keep the best result. Let's do it. C of 1. Only the 1 coin fits, so that's 1. C of 2. Again, just the 1 coin, giving us 2. Now, C of 3. This is where things get interesting. Both the 1 coin and the 3 coin work, but the 3 coin gives us 1 plus C of 0, which is just 1. way better than going through the one coin path. C of 4. The 4 coin takes us straight to 0, so that's also 1. C of 5. The best we can do is 1 plus C of 4, which gives us 2. And finally, C of 6. 1 plus C of 3 equals 2. So we know the answer is 2 coins. But which 2 coins did we actually use? That's where backtracking comes in. The idea is that while we were filling in the table, we also kept track of which coin gave us the best result at each step. At amount 6, the 3 coin was optimal, so we jump back to amount 3. At amount 3, the 3 coin was optimal again, so we jump back to 0. And there's our answer. 3 plus 3 2 coins, exactly as expected. This whole idea of recording your choices and then tracing back through them is a technique you're going to see over and over again in dynamic programming. So let's take a step back and look at what we just did. Visualize the problem, find the right subproblem, figure out how they connect, generalize the relationship, and implement it by filling in a table. 5 steps, same framework, and it works every time. Now, let's put this exact same process to the test on a harder problem, one with a completely different shape. You're given 2 strings, and you need to figure out exactly how many operations it takes to turn the first string into the second. The only moves you can make are inserting a character, deleting a character, or replacing a character. Let's start simple, transforming cat into car. We just replace the T with an R. 1 operation. Easy enough. But what about transforming kitten into sitting? That's noticeably harder to just eyeball. The answer actually turns out to be 3, but take a second and try to figure out which 3 edits you'd make. This is the classic edit distance problem. It's everywhere. Every spell checker uses a variation of this exact algorithm. When you type TE and it autocorrects to the, it's rapidly calculating the edit distance between what you typed and every word in its dictionary to find the closest match. So, how do we actually write an algorithm to solve this for any 2 strings? Trying to keep track of every possible combination of insertions, deletions, and replacements gets overwhelming fast. Let's run it through our 5-step framework. Step 1. Visualize. Instead of staring at the whole word, let's just look at the very first character of both strings. If those characters match, great. We don't have to do anything, and we can just move on to comparing the rest of the string. But when they don't match, we have to make a choice to fix it. Insert, delete, or replace. Notice what happens every time we make one of those choices. We chop a character off the front of one or both strings, leaving us with a slightly smaller pair of strings to compare. Because we're shrinking 2 strings simultaneously, this heavily implies we're dealing with a 2D structure. Step 2. Find the subproblem. What's actually changing here? It's the lengths of our 2 strings. So a natural subproblem is to define E of I and j as the edit distance between a string A of length I and a string B of length j. Our ultimate goal is to find E of 67, since kitten has 6 characters and sitting has 7. For base cases, if string A is completely empty, the only way to match string B is to just insert all of B's characters. And if string B is empty, we just delete all of A's characters. Step 3. Find the relationship.
To compute E of I and j, we just look at the first characters of our current strings. If they match, it's free. The cost is just whatever the edit distance was for the rest of the strings, E of I-1 and j-1. If they don't match, we have 3 choices, and each one costs exactly 1 operation. If we replace a character, we consume a character from both strings, moving us diagonally, 1 plus E of I-1, j-1. If we delete a character from A, we move straight up, 1 plus E of I-1, j. And if we insert a character into A, we move left. 1 plus e of ij minus 1. We just calculate all three and greedily pick the minimum. Step 4. Generalize. Putting that together gives us our piecewise function. If the characters match, carry over the diagonal value. If they don't, take 1 plus the minimum of your three neighbors, top, left, and diagonal. And finally, step 5. Implement. This problem naturally maps to a 2D grid. We can place string A along the vertical axis and string B along the horizontal. Because every single cell only relies on the three cells immediately to its top, left, and diagonal, we can just fill this grid row by row, from left to right, top to bottom. By the time we reach any cell, its dependencies are already calculated. And when we hit the bottom right corner, there's our answer. 3 operations. The hardest part of any DP problem, by far, is step 2, finding the right subproblem. Everything else kind of flows once you nail that. And after solving enough of these, you start noticing something interesting. Most of them fall into a small number of recurring patterns. The first pattern is prefix DP. Your input is a sequence, and the subproblem is simply, what's the answer for the first I elements? We saw this already in coin change, climbing stairs, house robber, decode ways. They all follow the same shape. You're basically just working with a one-dimensional array and filling it from left to right. The second pattern is sorted prefix DP. Same idea, but before applying DP, you sort the input in a useful order. This shows up in problems like weighted job scheduling, box stacking, longest chain of pairs, and sometimes LIS-style problems. You just sort it first so that the dependencies only go in one direction. The third pattern is 2 sequences DP. Now your state depends on prefixes of 2 inputs. We just saw this with edit distance. Longest common subsequence is another classic example. The DP table is usually 2-dimensional, DP of ij. The fourth pattern is interval DP. Here the subproblem is no longer a prefix. Instead, it's a contiguous range from I to j. Matrix chain multiplication follows this pattern. So do problems like burst balloons and many palindrome-related DP problems.
And the fifth pattern is grid DP. Your input is already 2-dimensional, and each state represents a cell in the grid. Unique paths, minimum path sum, maximal square, all of them fit this structure. Now these aren't the only DP patterns that exist, but they cover a huge percentage of problems you'll encounter early on. Dynamic programming has a reputation for being hard, and parts of it are hard. Finding the right subproblem takes practice and intuition that really only comes from solving real problems. But the framework never changes. Visualize, subproblem, recurrence, generalize, implement. Every DP problem follows that exact same skeleton. The more problems you solve, the faster that pattern recognition gets. And eventually, you look at a problem that would have completely frozen you 6 months ago, and the subproblem will just be obvious. If this video helped you, consider subscribing. We go deep on the stuff that actually matters. See you in the next one.